Welcome back, everybody, to the second half of this session. This is the second day of recent trends in algorithms. And this talk will be a continuation of the talk that we heard yesterday from Diptarka Chakraborty. In case you missed it earlier, he's a faculty member currently at the National University of Singapore with wide-ranging research interests within theoretical computer science. Yesterday, he told us about the aggregation problem, starting with strings, and he left us on quite an interesting cliffhanger where we also talked about variation of a related question in the context of rankings, and now he will walk us through the solutions, I think is what was promised for the various questions he raised yesterday. So Diptarka, all yours. Thank you.
Okay. Thanks, Nildara. Yeah, so this is a continuation of yesterday's talk. So yesterday what I did was essentially I introduced you to a set of problems, and I promised that solutions of some of the problems I will discuss today. So yesterday I did not go into the technical details much. I mean, we just have some very basic observations. Other than that, there was not much technical thing. But today it will be completely technical, and we will see a few techniques to attack some of the problems we introduced yesterday. So yeah, so before starting, I mean, please feel free to stop, I mean, wherever, if you have any doubt or anything. So let's start recalling, I mean, where we ended last time. So we defined this median string problem. So what was the problem? So let's recall. So we are given a set of strings, x1 up to xm, over some alphabet sigma. And then we want to find a string y that minimizes the following objective, which is the sum of edit distance. Okay. And you should notice here that when I ask to minimize y, so here the y is from the ambient space. It could be any arbitrary string, so need not be from the input set. And if suppose y star be a string that minimizes this objective value, so then we refer y star as median. So yesterday we have seen 4 questions. So first one was like how to do clustering efficiently, which I already told that we are not going to see, I mean, answer this question in this talk. And then the second was how to perform approximate trace reconstruction. So I will, so yeah, those who can't remember this definition of approximate trace reconstruction, don't worry, because whenever I will talk about the solution of this problem, then I will define it again. And then the third question was, what is the connection between approximate trace reconstruction and the approximate median problem? And then the last, not the least, the question was how to find an approximate median efficiently. And then we have basically seen that using just the triangular inequality, we get a 2-factor approximation. And if we restrict ourselves to some special case, like when the metric space is Hamming, so then this problem is very trivial. I mean, we can easily get the exact solution in polynomial time, actually linear time. And then we went to another type of special case or restricted case where our inputs are not just arbitrary strings, but permutations. And from there, we define the rank aggregation problem. So what was the problem? So it is exactly the median problem. So only difference is that now the input strings are not just arbitrary strings, but rather permutations or rankings. I mean, yesterday, we have seen that permutations and rankings are essentially the same. And then the question was, I mean, can I find a permutation y that minimizes the sum of distances? Okay. And that's why, I mean, if you recall, I also mentioned that since now we are asked to find a permutation, specifically not just arbitrary string, So it is not really a special case of edit median. Okay. So now what we know so far. So there was another dissimilarity measure that was defined on permutations or ranking. So that was Kendall tau. And with respect to that, we know that the problem is NP-hard, even for 4 inputs. On the other hand, we know PETAS. And for 3 inputs, we don't know whether it is NP-hard or it can be solved in polynomial time. But for Ulam, we don't know much actually. So unfortunately, we don't even know that whether the problem is NP-hard. Although I believe that it is NP-hard, but we don't know. On the upper bound side, so before our work with this Dash and Krautgammer, we did not have any result on the Ulam median, I mean better than 2 approximation. So what we show that we can actually get 2 minus epsilon approximation for some small epsilon in polytime. And interestingly, we also show that for 3 inputs, actually, we can solve it exactly in polytime. So then you can see that this Kendall tau metric and Ulam metric are really different in that sense, because for Kendall tau, for 3 inputs, we don't know anything. But now for Ulam metric, we know that it is in P. So let's now focus on these 2 results. And so this second result was not very difficult. So let me start with that. So how do I compute median for 3 inputs? So here was a very high level idea. So the algorithm will be basically 2-phase algorithm. So in the first phase, I will relax the constraint and finds a solution that need not be a permutation. So if you recall that the difference between the edit median and the Ulam median was that the output for Ulam median must be a permutation. But for edit median, that was not the case. So our first phase here, I will relax. So basically, I will remove that constraint that the output must be a permutation. And then in the phase 2, we round this relaxed solution into a feasible one. So basically a permutation. Okay, so I will round it to a permutation. So yeah, so in the very high level, you can think it, I mean, you can find it very similar to like what we did for integer programming. To solve integer programming, first we relax it, I mean, consider the LP relaxation and solve this linear program and then do some kind of rounding. So yeah, so at the very high level, you can also see these 2 phases in the similar way. So now let's focus on the phase 1. So as I mentioned, I remove the constraint that the output is a permutation. Okay, so now we can we are free to output any arbitrary string. And what is the advantage here of doing this relaxation is because if you recall, yesterday I mentioned that for edit median, we can have we can construct a very simple dynamic programming algorithm which runs in exponential time, so exponential in the number of inputs. Now, as long as our inputs is constant, then this is a polytime algorithm. So for example, so here we are only interested in finding median for 3 inputs. So then if you replace m by 3, so then it is just a cubic algorithm. So that is the advantage we get from doing this relaxation. So basically, we can now use that dynamic programming algorithm. But actually, what we did is like not just we relax to arbitrary string, but we add one constraint. I mean, we remove this constraint that the output is permutation, but we add one slightly simpler constraint is that the output should be of length n. So if you recall that we are now, so our inputs, all our 3 inputs are basically permutations from 1 to n. So these are n length string. And I add this constraint that our output should be n length solution. And it is actually not very difficult to modify the dynamic programming algorithm to output the n length solution. So yeah, so here I just I'm not going to explain the dynamic programming algorithm, because you can believe me that it is not that difficult, and if you spend some half an hour, you could figure out by yourself. So that's why I just post this as exercise. So the first exercise is try to design this dynamic programming algorithm that outputs edit median, okay, without any constraint on the output. And then second exercise is try to modify it and add this constraint that the output has to be of n length. And even after modifying this dynamic programming, still it runs in polynomial time as long as your number of inputs is constant. So for m equals to 3, it will be a polytime algorithm. Okay, so that's the end of the first phase. So now, how do we round it? So what is the problem that could arise? So these are suppose inputs. We have x1, x2, x3, x4, and so on. Okay, so although I already mentioned that we are interested in like 3 permutation case, but I mean, I just whatever I draw here is basically for arbitrary number of permutations. So basically try to explain to you that what problem that could occur when we relax this, basically remove this constraint that the output is a permutation. So when we apply this phase 1, basically this dynamic programming algorithm, so then the output need not be a permutation. And since it is, I mean, I also add this constraint that this has to be of length n. So essentially there could be some duplicates. Okay. So for example, here you can see that both the symbol 1 and 2, they occurs twice. And now phase 2 will essentially be that I have to remove these duplicates. And since they are of n length, so this is also of length n. So if there are duplicates, then there has to be some of the symbols which are missing. So I have to remove the duplicates and get back those missing symbols to make it a permutation. And that is my job to do in phase 2. Okay, so basically we have to round this relaxed solution to a feasible permutation. And we have to delete these duplicate symbols and insert missing ones cleverly. I mean, if we do arbitrarily, we may not be able to get a good solution. Okay, so this is the high level idea of the phase 2. And now how this argument works. I mean, this is again very similar to what we do for LP and ILP. So consider this following 2 quantities. So the first one is what is our target. So that is the optimal permutation. So I mention it by opt rank. Okay. So the optimum value obtained by a permutation. And now the second quantity is opt n length. So which basically our phase 1 outputs. That optimum value attained by any n length permutation, n length string. And since this n length, so this is of course a relaxed version of the rank. So that's why whatever be the optimum value attained by n length string would be at most the optimum value attained by permutation. So that's why the opt n length is at most opt rank. Okay, this is a very simple observation. And now suppose y bar attains this n length optimum. So now phase 2 will transform y bar to some permutation z. And now what we want to show is that whatever be the objective value, so basically sum of distances from the z is at most some c times objective value from y bar. Okay, and since y bar is our optimum solution for n length version, so then this is essentially give us that this is equal to c times opt n length, and then I will use this simple observation to get an upper bound on C times opt rank. And then just by definition of approximation, this gives C approximation. So this Z will give us C approximation because this is C times opt of rank. Okay, so this will be the very high level idea, and this is exactly, as you can see, that this is exactly same as how we argue for LP relaxation. Okay, so now what will be our rounding technique here? So as I mentioned that I want to, I mean, we show that for 3 inputs, the Ulam median we can find in polytime. So basically we have to output some exact median. So there is no scope of approximation in our result. So that's why what we essentially show is that in the after phase 2, whatever Z we get, so the objective value with respect to Z is at most the objective value with respect to Y bar. So this Y bar is n length optimum. Okay. So this obtain the n length optimum. So essentially we show this claim for basically C equals to 1. Okay. And 1, as you can see that now once we show this, then just by whatever argument we did in this last slide, so then we basically get a ranking which is optimum rank aggregation. Okay, so now how do we proceed? So how do we show this claim that after phase 2, whatever we get, so the objective value is at most the objective value of Y bar. So to do that, so this is how our argument works. So let's first fix an arbitrary optimal alignment between Y bar and X1, X2, X3. Okay, so here are suppose X1, X2, X3. So these are some permutation. Suppose 1, 2, I don't know, something. So maybe 1, so 2, suppose here it is 4, 3, here maybe 3, 4, and something else. And here maybe start with 3, 2, 1, and something. And now what we get, suppose Y bar, this is say 1, 2. And now fix an arbitrary optimal alignment. So what is an alignment? So this captures the set of edit operation essentially. So alignments is basically a mapping. So suppose, so what is the alignment between in this example? So suppose I take X1 and Y bar. So maybe optimal alignment is I will match 1 with 1, 2 with 1, and maybe here I find mismatch. So maybe I delete this character and also maybe delete this character. Okay, so the set of matchings are basically this alignment. And now for each duplicate symbol, what we do is that we only keep the occurrence with maximum matches, okay, with respect to this alignment that we considered in the here in the first line. So for example, here, say for this symbol 1, so it matches in, so this first occurrence of 1 matches with 2 strings. Whereas the second occurrence of 1 matches with only 1 string. So what I do is that I will keep this first occurrence and I will delete the second one. Okay. And now what we get from doing this? So what we get is that our objective value, I mean, once I delete this 1, so basically we start with Y bar, which has 1, 2, 2, 1, and so on. Now after deleting 1, suppose in the intermediate step, say I get 1, 2, 2. So 1 is not present. So now when I consider the distance, the edit distance between now Y bar prime with these three things, what will happen? So the objective value will increase by 1 for one input, because this particular one previously matched with x3, but now I delete it. So that means when I try to define an optimum alignment with this y bar with x3, so then I have to pay one extra cost, because this one is not present, I have to insert it. So that's how the objective value now increased by 1. But we also gain something, because this particular one was not matched with any of the character in x1 and x2, because the one, since both x1 and x2 are permutation, I know that one occurs only once there. And this particular one was matched with the first occurrence. So then in the cost, I have to delete this one for both x1 and x2. And now since in the y bar, I delete one, so those deletion cost I don't have to pay. So that's why I get this advantage of 2. So basically I increase the objective value for 1 for x3, but for x1 and x2, I decrease the objective value by 2. Okay. And similarly, now if we consider that after deleting all the duplicate symbol, we also have to insert back the missing symbols, right? And now for the missing symbols, what we can do is the following. So we will insert these missing symbols in such a way that it maintains at least one input. I mean, it will match with one input. So for example, so again, suppose x1, x2, x3, and something 1, 2, maybe 3, and so on. 1, 2, 4, 3. So here 3, 4, so on. Maybe 4, 3, 1, 2, something. And now after deleting whatever set of duplicate characters, so whatever the intermediate step, I mean intermediate string I get, maybe it contains 1, 2, but maybe no 3. Okay. So maybe it contains 4, but 3 is missing, suppose. Okay. I don't have 3 here. So now while inserting that 3, I can always ensure that it will match with one particular string, because I will just choose one arbitrary string, maybe say x1, and look into where this 1, 2, everything is matched. And now wherever this 3 occurs, and whatever be the last symbol before 3 that was matched with here, I will figure out that position. And just after that, I will, so suppose this position, this particular guy was matched. And now just after that, I will place 3. So then definitely 3 will be matched in x1. So 3 need not be matched in x2 or x3, but that is fine. And why that is fine? Because again, by a similar type of argument that we did for the removal of duplicate character, you can see that the objective value, by after inserting these new symbols, decrease by 1 for this matched string. So for x1, since I maintain the match for 3, so there the objective value decrease. But it will increase for the other 2, because other 2 there may not be any match for 3. The way I place it in the y bar. Okay, but that is perfectly fine for us. Why? Because now if you see here, so what we did is that for each deletion of the duplicates, I increase the objective by 1 and decrease by 2. Okay, so basically +1 -2. So overall -1. But while inserting back the missing symbols, I decrease by decrease by 1. So -1 +2. So basically +1. But since our restriction was that our output is n length, so if you count the number of duplicate entries, that is exactly equal to the number of missing symbols. So that's why, after performing these 2 steps, whatever be the minus, I mean, if suppose there are duplicate entries, C, say C duplicate entries, so then this, I will get this term minus C, and for missing symbol, I will get plus C. So they will cancel out, and I will, the objective value basically stays the same. Okay. So, yeah, any doubt so far? Because that is the argument here. Yeah, if you have any question, you can ask me now, maybe. Okay, seems there is no question. Okay, so that's the reason, I mean, why the objective value stays the same. And then essentially, we get our claim that the objective value of with respect to Z is at most the objective value with respect to Y prime. And as a result, we get exact solution after rounding. Okay. So this argument actually also can be extended for constantly many inputs because phase one runs in polytime as long as the number of inputs is constant. Okay. So, but the problem will arise in this rounding phase. So since previously, I mean, there are 3 inputs, so that's why we were getting this type of nice bound that +1 -2 and one case -2 +1. But now that argument will not work if there are constant number of strings. But still, I mean, one can slightly do more careful analysis and can show that it can be increased only by a factor of 3/2. And that's why we get a 3/2 approximation algorithm as long as the number of inputs is constant. And moreover, this this similar type of approach also works for the center problem. Okay, so basically later, I mean, after our work with Dash Krautkammer, later with Gajjar and Jha, so we extended it to center problem. So just a slight detour from here is that what was the center problem? So the center problem is basically the max version. So for the median, we were minimizing the sum, but in the center, we are minimizing the max distance. Okay, so the other things remains exactly the same. So only the objective value is different. And unlike the median problem, so where for Ulam median, we don't know whether it is NP complete or not, but for center problem, we know that this is NP complete. So what we show is that essentially the similar type of approach work for this Ulam center for constantly many inputs. Like the phase one remains same, like still find a n-length center string, and again we can design a dynamic programming algorithm. So this dynamic programming algorithm is slightly different than the median one, but we can still do it. And rounding, again we can do rounding, but the rounding will not be as simple as the median one. But we essentially show that in the rounding phase, essentially that rounding phase is solving another center problem. I mean, center problem with respect to another metric, which is Hamming metric. But here it is with the presence of wildcard, not just Hamming, normal Hamming metric. So this is basically center problem with Hamming with wildcard. And that particular version also we can solve in polytime as long as the number of inputs is constant. And we can again get the 3/2 approximation. And for 3 inputs, we get exact. So yeah, so I'm not going to the details because I'm not planning to do that in this talk. Maybe you are welcome to read our paper. But the high level idea was the same. Okay, so now we will try to extend this to the arbitrary inputs. So now, so far, if you have any question on this, whatever I discussed so far, maybe this is a good time to ask, because now I will describe a different technique. Since there is no question. Okay, so what we argued so far is that for constantly many inputs, we can get to 1.5 approximation in polytype. But what if our number of inputs are arbitrary? So will the similar type of approach work? Well, the similar type of approach will definitely work, because finally we'll get 1.5 approximation. But the problem is this phase one. So in the phase one, where we relax this constraint and we were using the dynamic programming algorithm for edit median, so that runs in exponential time. Okay, so exponential in the number of inputs. So if M is arbitrary, then there's no longer a polytime algorithm. So the second phase for the Ulam median, so the way we do this rounding, that part is still polytime, even for arbitrary number of inputs, but the phase one no longer polytime. So so this whole approach fails if we want to achieve some 2 minus epsilon approximation in polytime. So that's why we used different techniques in achieving that result. Okay. So for that purpose, so let me first divide this into two cases. So the first case is we call high regime. So what is high regime? So basically, suppose consider the case where the optimum value is large. So basically omega mn. So recall that m is the number of inputs, so number of permutation we are given, and n is the length of each input. So these permutations are from 1 to n. And now, suppose the optimum objective value is, say, mn by some constant, say 10. So then we want to claim that in this particular scenario, if I output the best input, that actually breaks two factor. So yesterday I argued that any based input will give 2 approximation. And that works for any metric. But now today what I want to argue is that if we consider the Ulam metric and the objective, I mean the optimum objective value is large, so then based input itself will break the 2 factor. It will give me some 2 minus epsilon for very small epsilon. Okay, so epsilon is basically some constant greater than 0. So yeah, so just to emphasize that, I mentioned that it is independent of n and m. So how do we, so now as you can see that from this claim that there is nothing clever algorithmically here. So whatever should be like analytically. So we have to analyze it in cleverly such that we can show that based input itself breaks the 2 factor. So let's first try to argue about that. Okay. So to argue about that, first make a simple assumption that none of the input is very close to this unknown median. So whenever I am given this input set S, so there is some median, right? Some optimal median Y star. We just don't know. And now assume that none of the input is actually close to that. So pictorially, so basically, if you look into this ball of radius 1 minus epsilon opt by m around this unknown median, so then none of the input lies within that ball. So everything is outside. And why? Basically, we can make this assumption without loss of generality. And why? Because if not, then that particular input will break the 2 factor. Because suppose if there is something here which is of distance at most 1 minus epsilon, then just by exactly the same argument we used yesterday using triangular inequality that shows the 2 approximation, just using the similar type of argument, we can show that this particular input will break the 2 factor. Okay. So let's now make that assumption that within this 1 minus epsilon opt by m radius ball, there is no input. And again, recall that our high regime is when opt value is mn by 10. So that's why I just replace, instead of opt, for simplicity, I just replace by 1 minus epsilon n by 10. Okay.
So sorry,
Yeah.
maybe this is a silly question, but it's a quick one. Does the algorithm know how to distinguish between the high regime and the other regime? As in, can we
No.
figure out? No. So
No.
all this is in the analysis, right?
Yes.
Okay. So the without loss of generality part, where you said that there exists an input which breaks the two factor. That
No,
is
so
also
the
something.
assumption is this one, that none of the input is actually close to y star.
Oh, I see. So algorithm is not under any obligation to return this point in this case. Right. Okay. Okay,
So
yeah,
here, so here we are just saying that there is no input that is close to y star, because if that is, because if you run the, if you output the best input, definitely you will also consider this point while computing the objective. So then definitely, whatever you get is better than the objective value attained by this particular point. So you will break the two factor.
Okay, I see. Okay, that makes sense. Sorry,
yeah, so that is the purpose of this assumption.
Right. Makes sense.
So still we are in the high regime. Okay. So now, what does this high regime now then means? So then, if I consider, if I make this assumption that inside this ball there is no point, so then I know that so from this unknown median to any of the input, there are set of edit operation I have to perform, and the edit distance is greater than essentially n by 10. Okay, so it is 1 minus epsilon n by 10. So for simplicity, I just make it n by say 15. And now this for each of these inputs, I associate this set. So everything is for analysis purpose. I cannot actually see this set because I don't know the median. So for each, with each of these inputs, there is an associated set. And what is this set? So this set contains all the symbols that has to be deleted and inserted with respect to this optimal alignment. Okay, so you fix the one particular, some arbitrary optimal alignment from this y star to each of this input, and now there will be definitely some of the symbols has to be deleted and inserted, and this II, so that basically denotes that those set of symbols. Okay, and since I already assume that there is nothing inside this ball, so then I know that this set of symbols has to be large. So for each of the input, whatever be the associated II, so this size has to be large because those edit operation has to be performed. Okay, so maybe, well, so so actually, so since I am considering II to be the set of symbols, so in the actual distance, you will count insertion and deletion twice. So for now, for simplicity, let's make this, this is like another without loss of generality. So here, when I consider the edit distance, I basically count the insertion and deletion together. So because this is a very simple thing, because otherwise just instead of 20 I will get, instead of 10 I will get 20. So everything will remain the same. So as long as those are just constant. Okay, so then basically, so for each of these unaligned, set of unalignment character is say n by 50. Okay. So now, here you can see that for each point there is a set of unaligned character, and these are of size at least n by 50. Now the claim is that there can be at most 30 such possible set, such that all the pairwise intersection is of size at most n by 450. You may wonder, where from this constant comes. So essentially, if here you take n by c, so then you can prove that there could be at most 2c such possible set, such that the pairwise intersection of these sets is at most 2c n by 2c square. Okay, each set is of size at least n by c, and if the pairwise intersection is at most n by 2c square, both this condition could be satisfied by at most 2c such set. There cannot be more than such set. And this claim is not very difficult to prove. It can be very simply proved by simple inclusion-exclusion argument. And once we prove that claim, then what it implies the following. So let's make this another assumption, another observation. So if I consider any two permutation, xi and xj, what is the edit distance? So edit distance is at most, so if I consider, so here my xi and here is xj, and suppose this is my y star, and I know the set of unaligned character is I and ij. I know that what, I can get a simple bound from the edit distance between xi and xj. What is that simple bound? Because I can go via this y star, that is the most naive bound. So basically I first delete this I thing, and then perform this edit operation that involve the symbols in ij. But now if you look into these characters, whatever be the characters that are common in ii and ij, so that I have to delete from xi once, and then I can directly add it in the xj. So I don't have to go via y star for those symbols. And that's how in the distance I will save this factor of ia intersection ij. Okay, so the edit distance will now becomes whatever be the size of the ii, ij minus this intersection size. And now what it implies now with whatever we observe, that there could be at most 30 such set, such that the pairwise intersection is small. Then now if you look into this ball of slightly larger radius than n by 10, so then whatever
sorry again, if the pairwise intersections are small, then is the intuition that the edit distance is large because you're subtracting less?
Yes,
I see.
so,
but like you said, this is also like an upper bound, right? So the
yes.
edit distance between xi xj could be much smaller than this bound, right?
Yes,
I see.
So basically it is saying that if the intersection is large, so when intersection is small, we cannot say anything, because this is an upper bound.
Yes.
So when the intersection is large, then the edit distance will be small.
Okay, right. Okay, so it makes sense. So the number of sets whose pairwise intersection is small is bounded. So for many of them, it's going to be large. So you're, so I guess you want to say that many of the input points themselves are close to each other. Or
exactly.
Something like
exactly.
Great. Makes sense.
So yeah, so pictorially what we get is that if you look into whatever be the points inside this outer ball, they just form some constantly many clusters, essentially 30 clusters. And what are these clusters? So in this cluster, if you look into, and along with a body point, so this is just some fancy name we just came up with. So this is basically the set, as I mentioned earlier, that I can get at most 30 such set, and this set are associated with some point. So those point I call the body point. Okay. So for example, so now suppose this is a body point for this red cluster, this is body point for the purple one, yellow one, and the green one. And now all the other points has to be in one of this cluster. So there could be many other points, but they must be in one of the cluster. And then what is the distance from, if you look into any point in a cluster to its corresponding body point, what is the distance? We will use this inequality. So that distance will become ij minus the intersection. And I know that for each of these points, the intersection has to be, so suppose this is my, say, xj. I know that I1 intersect ij, so this intersection has to be greater than n by some 450. So then I know that edit distance between x1 and xj, that has to be this whatever twice roughly, I mean, this is some rough calculation. So I mean, yeah, so this is n by 15 minus n by 450. So which is basically better than 2 factor. So I get 2 minus 130 by n by 50. Okay. And now there are some constantly many clusters. So then by averaging argument, I know that one of the cluster will contribute some constant mass on the unknown optimum, right? So whatever be the opt, so in that particular quantity, one of the cluster will contribute constant mass. Say constant, I just take 70. And now, so if you consider the body point corresponding to that such a largest cluster, so then for that particular, I mean, its own cluster, it will break 2 factor. It will achieve 2 minus 1 over 30. And for the remaining, it essentially maintains the 2 factor. I mean, this again has to be proved formally. So I am not going to give the exact all the technical details, but this is the rough idea. So for its own cluster, it will break 2 factor. For the remaining cluster, it will maintain the 2 factor. So, and that's why, I mean, as a whole, when you take the sum with respect to this y bar, it attains to minus epsilon approximation. So basically it breaks 2 factor. Okay, so is this idea clear? Yeah, so there are a lot of technical details that I hide just under the rug, because one has to also cleverly choose this body point so that they can argue that it will maintain, first of all, it will give you this 2 minus 130 approx for its own cluster. And also, so this is pretty simple to show that, I mean, for the remaining, it is roughly 2. I mean, it will be slightly more than 2, but it will be roughly 2 approx for the remaining points. And so when you take the final sum, it will be 2 minus epsilon. And this epsilon will be like really very small, because you can now see that there is only, I say, 1 by 30, and that is also for this 1 over 70 fraction of mass. So that's why you can imagine that epsilon is very small. So this is the whole argument. But that was the case for high regime. So I have not tell you anything about the low regime case. Okay, so the high regime only says that the best input achieves 2 minus epsilon. But as Nilhara pointed out some before that, I mean, we cannot really distinguish between the high regime and low regime. I mean, we have to design our algorithm in such a way that the output breaks 2 factor. So now let's consider the small regime separately for now. So consider the small regime case is that the opt value is small. So yeah, so here by small, I mean, what is the quantity I have not mentioned. And also make another assumption. This is definitely not a without loss of generality. So this is just like some kind of extreme case that suppose this optimum cost is distributed over almost all the symbols equally. So I mean, optimum cost you can count in two ways, right? So this was sum of edit distance. And you can also think of like this as a sum over the symbols. So basically for each symbol, how many times you have to insert and delete. So now, if this cost is distributed equally among all the symbols, then suppose this opt value is at most, say, mn by 10, right? So then for each of the symbols, roughly you will get that for m by 10 strings, they will be unaligned. So if they are, so suppose, okay, so let me now draw here. So suppose these are my x1, x2, and so on. And suppose this is my y star. And if I consider one particular symbol, so if the cost is distributed among all the symbols, then what is the cost contributed by symbol, each of this symbol? It is m by 10. So what does that mean? That means that it will be unaligned in only m by 10 many inputs. For remaining, it will be matched. So now if you consider a pair of symbols, A and B, so B will also be not aligned in some set of inputs, which is also m by 10. So now if you look into the pair, so then except this like bad inputs, everywhere else A and B will be matched. And if A and B are matched in all the remaining inputs, then the relative ordering also has to be same as it was in this unknown y star. So the relative ordering will be same in m minus 2m by 10. Right? So basically 4/5 fraction of the inputs, the relative ordering will be same. And thus now if we can, for each pair of symbols, if I can check the relative ordering among all the input permutation, we will retrieve back the actual y star. Because I mean, if we can retrieve back relative ordering of all the pairs, then just by doing topological sorting, we can retrieve back this unknown y star. Okay. So, but the problem is, of course, that this is a very strict assumption that I make, that the cost is distributed everywhere. And also like for each pair, I will be able to get the relative ordering correctly. So which may not be the case. So these are the issues that could arise, that maybe for some pair of symbols, the relative orderings in majority of the inputs are really bad, because maybe they are unaligned in most of the inputs. And that could be due to just a few bad symbols, because a few bad symbols creates problem for several pairs. So that's why, I mean, those cases has to be handled, and we actually handle by removing some of the cycle, by constructing the, I mean, by considering the corresponding graph. So here, what is the graph? So graph is basically the vertices are the set of symbols, 1, 2, 3, up to n. And now I will add an edge from 1 to 3 if I see that 1 occurs before 3 in majority of the input. And that is how I build the graph. And now, since there are few bad symbols, So there could be, I mean, if there are no cycles, then actually we are in a good shape. We can perform topological sorting. But there could be some cycles, so we have to remove the cycle. So yeah, so I am not going into again the details of all these things. So we can essentially remove the cycles, and then finally we can perform the topological sorting. But this still that one issue still remains is that how to merge these high and small regime cases, because we cannot distinguish between two things. So that's why it will not be like the algorithm will, I mean, we really don't apply the algorithm in this way, that for high regime, if high regime, we apply this algorithm, for low regime, we apply this algorithm. So that will not be the argument. I mean, we have to merge these two. So basically there will be two algorithms. One will consider this graph and perform the whatever the removal of cycle and the topological sorting, and another will be the best of input. And now, so the analysis should take care of the fact that even if they are like something in between case, like high and this special type of small regime, still the best of these two algorithm will break two factor. And yeah, so there are lots of technical details and it is not possible to cover in this talk. So you are welcome to read our paper. But what our analysis actually give us is since all this thing has to be taken care of, like removing the, I mean, there are basically two algorithms and two of this algorithm gives two different approximation guarantee, and we have to basically equate them to optimize. And so that's why finally whatever epsilon we get is like very small. So we will break two factor, but by a very small amount. So essentially you can think of this like 1.99999 something. So it is not like 1.5 or something. Okay, so that's the end of the story for this Ulam median algorithm. And just I want to make a few open problems. So first of all, can we get a p-task for the Ulam median? Second, can we show that Ulam median is NP-hard? And ideally, we want to show this NP-hardness for constantly many inputs. And I don't know whether that is at all true. And then third one is that can we extend this result to edit median? I mean, I must say that, I mean, like this high regime case, that actually could be lifted to edit median under certain assumptions. So, but we don't really know, I mean, how to leave the small regime case. So yeah, so this I want to pose as another open problem. Okay, so any questions so far? So yeah, so this is not the end of the talk. So I will take a couple of minutes to talk about something else.
So the NP hardness is not known even for non-constant many inputs.
Yeah. No.
Right. Okay. So yeah, I just wanted to clarify that maybe because of the Kendall Tau result, you are hoping that there is a NP hardness even for constant many inputs. Right. Okay. Yeah. Thanks. Yeah. Please go ahead. Yeah.
Okay. So yeah, maybe I will take another 5 minutes. So now there is also another set of problems that I promised that I will give you solution today, but I am not going to give you solution because I am almost out of time. But I just want to give you like what is the result we can get. So if you recall that yesterday I started introducing this median problem by first talking about this DNA storage application, and there essentially the problem we encountered was the trace reconstruction problem. And for the trace reconstruction problem, I mean, our channel was insertion deletion channel. And we were interested in the average case version because I mentioned that for DNA storage, it roughly suffices to solve the trace reconstruction problem for the average case. And there are several results known, and for exact trace reconstruction, we know some lower bound on the number of samples, and whatever be the upper bound, that is not really very good. So now we ask this question that what about approximation? Suppose instead of exact trace reconstruction, I ask you to reconstruct something which is close to the unknown string. What can I do? So we actually show that to solve this problem, just using 3 traces, we can get we can reconstruct some string which is p square n at distance, p square n. So it is not exactly p square n, some p square log 1 over pn with high probability. And this reconstruction we can do in near linear time and deterministically. And how we show this result is by basically answering this question. So if you recall that last time I asked this question that what is the connection between approximate trace reconstruction and approximate median? Although in practice I mentioned that people use as a heuristic this approximate median finding algorithm to solve the approximate trace, but so far we do not know any concrete connection. So what we show is that at least, they are same at least in the average case. What we show that if you take any approximate median like 1 plus epsilon approximate median, so then with high probability, they are very close to this unknown string X. And then basically result 2 implies result 1. Yeah, so now I am going to skip this. So essentially, we will argue that, okay, so if I could find the exact median, so since we consider only 3 traces, so then I can use the dynamic programming, and in cubic time, I find the exact median. And just by result 2, I get that that has to be very close to the unknown string. So basically in cubic time, I can reconstruct. And then we can actually make this algorithm even faster. So by some clever technique, not just run the dynamic programming, but make divide it into blocks and run the dynamic programming independently on each block, and then finally concatenating them. And that is how we can reduce our running time of the algorithm to near linear. Okay, so I am out of time, so I am going to skip everything from now on. Yeah, so, and I just want to pose another open problem is that whatever result we get works for 3 inputs, but can we really reduce the error by increasing the number of traces? And another open problem is can we get the similar result for worst case? So all the our proof actually heavily relies on the fact that this is average case. So it is unlikely that we'll be able to directly extend to worst case, but maybe we can come up with some different argument. And that I want to pose as another open problem. Okay, so thanks. Yeah, any question?
All right, thank you so much, Diptarka, for that really beautiful talk. And on behalf of all the attendees, I'd like to thank you and a virtual applause for you. And welcome any questions in the chat. We are slightly over time, so in case we are not able to accommodate everything, please feel free to perhaps reach out over email in case you have any unanswered questions. Thank you.